I am Jawed Ahmad, Department of Mathematics, Jamshedpur Women's College. In the previous video, we have already discussed some topics of countable and uncountable sets. And in this video, we shall discuss some theorems related to countable and uncountable sets. As I have already told that this video is for the honors students of semester 2 paper 3 real analysis. Now we discuss the first theorem as a set A is countably infinite if and only if it can be put in the form of sequence A1, A2, A3 of distinct elements. This theorem can also be asked like this: a set A is said to be countably infinite, or is countably infinite or countable or denumerable or enumerable if its term can be listed as a distinct terms of the sequence. Now we try to prove this theorem. As the set A is given to be countably infinite, that is, let us suppose that the set A is countably infinite set, then by the if and only if there exists a 1-1 onto mapping F from N to A. We have already discussed in the previous video under what condition a set is said to be countably infinite or enumerable or denumerable. In that video, we have discussed or established the fact that a set is said to be countably infinite set if we are able to establish one-to-one correspondence of this set with the set n of natural numbers. That's why we write here a set A is countably infinite if and only if there exists a 1-1 onto map F from N to A. If and only if Fn1 is not equal to Fn2 for n1 is not equal to n2, and this is the condition for the function to be 1-1, and for any element B belongs to the codomain B belongs to the codomain A, there exists an element A belongs to N, that is the domain of the function, such that image of the function under F is B, and this is the condition for a function to be onto. If and only for any n belongs to N, there exists a n such that Fn is equal to N. Thus we have Fn is equal to N means F1 is A1, F2 is A2, F3 is A3. It states that for each natural number we get a distinct term of the sequence An. Thus we have A is equal to A1, A2, A3 and so on, where A1, A2, A3 and so on are the distinct terms of the sequence An, and hence the theorem proved. Now we discuss the second theorem. The union of two countable sets is countable. This question can also be asked from you students, that prove that the union of two denumerable sets is denumerable or enumerable sets is enumerable. Proof. Let A and B be two countable sets. We have to show that A union B is countable. Since A and B are countable sets, there are three possibilities. Number one, both sets are finite. One set is finite and the other is denumerable, and both the sets are denumerable. If out of two sets A and B, we will have three possibilities: either both sets are finite, or one set is finite or other is denumerable, and both the sets are denumerable. In case 1, obviously A union B is finite, and we know that a finite set is countable, and so we write here consequently countable. In case 2, we know that union of a finite set and a countable or denumerable set is countable. For case 3, let us assume that the set A is equal to is the set whose elements are A1, A2, A3 and so on, and another set B is equal to the set containing the elements B1, B2, B3 and so on. Then A union B is equal to A1, B1, A2, B2 and so on, or this set can be written in either order. Now we define a map F from N to A union B as Fn is equal to A n plus 1 by 2 if n is odd, and B n by 2 if n is even. And students can easily check that if you put n is equal to 1, you will get F1 is equal to A1. If you put n is equal to 3, then F3 is equal to A2. Just like if you take n as even, that is 2, then you will get F2 is equal to B1. So we see that for each natural number n, we get the elements of A union B. That is, each natural number is associated with every member of the set A union B. It means that the function is 1, 1. That we have written here like this. It can be easily shown that F is 1, 1 and on 2. This shows that A union B is countable, that is denumerable. Now a question like this can be asked from you students, that prove that the set I of integers is countable, or the set I of integers is countably infinite or denumerable or innumerable. Proof. Let n be the set of natural numbers. We know that an identity mapping F from n to n given by Fn is equal to n for all n belongs to the domain n, which is clearly 1, 1 and on 2, that is n is equivalent to n. This implies by definition n is denumerable, and this implies n is countable. So such question can also be asked from you students, that prove that the set n of natural number is countable, and students are advised to prove this like this. Let n minus be the set of negative natural numbers or negative of the natural numbers. Then we can define a map G such that, or a G from n to n minus. That is, we define a mapping G from n, that is set of natural number, to the set of either you say negative natural number or negative integers, given as Gn is equal to minus n for all n belongs to n. Here you can see also that G1 is minus 1, G2 is minus 2, G3 is minus 3. So each natural number corresponds a negative integer, and so clearly G is 1, 1 and on 2. This shows that n is equivalent to n minus. This implies n minus, that is the set of negative integers is denumerable, and denumerability implies the countability of a set, and this implies n minus is countable. We have proved that n, that is the set of positive integers, is countable and set of negative integers is countable, and now I is the union of n union set containing only 0 element, union n minus means negative integers. Set of integers, as you know, is the union of positive integers, negative integers, and the element 0. And we have already proved that n is countable and n minus is countable, and the set containing 0 is the singleton set, and it is already countable being a finite set. That we have written here, being countable, union of countable sets is countable, hence the set I of integers is countable. Now we take the next example. Prove that n cross n is countable, that is the proof that the Cartesian product of n with itself is countable. The elements of n cross n can be written as 1 1, 1 2, 1 3 and so on 1 n, 2 1, 2 2, 2 3 and so on 2 n, and dot 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 m1, m2, m3, mn and so on. Let us construct a set AI that is equal to the set of all ordered pairs whose first member is I and second member is 1, 2, 3, 4 and so on. Then n cross n is the arbitrary union of the sets AI, where AI intersection AJ is equal to 5 for I is not equal to J, and AI is countable infinite, countably infinite. Then union I runs from 1 to infinity, AI is countable because we know that countable union of countable sets is countable. Hence n cross n is countable, countably infinite. You should write countably infinite. And in the coming videos we shall discuss the rest topics of countable and uncountable set. Till then, stay home, stay safe. Thank you.